Good morning, everyone. In today's class, we'll start the revision what we have completed in the unit 1, right? So, regarding this unit 1, we just started with the solid state physics. So, what is the aim of solid state physics and why it is necessary to an engineering student to study about solid state physics? We just have a glance of it, right? So, we need to understand the solid state physics to explain the exact properties of the materials which is on the surface of the earth, and how these particular properties of solid materials can be known by means of the crystalline solids. See, again these solids has been classified into different categories that we are going to learn in detail, right? So now here we just have a very brief introduction about this chapter 1. So before going to this chapter 1, very briefly I will explain you what is actually the matter. On the matter is composed of three important states, that is gases, liquids and solids. So here we are giving our due importance to the solids. So gases and liquid crystals, that is we are not right. No, we are not talking about that. We just have a definition of that. So in the gas, we start with the gases. The atoms and molecules in the gas are not what you can say bonded to each other. So here they are freely moving. You can just see this schematic diagram where you will find that the atoms or molecules are away from each other. So this arrangement of the atoms probably is said to be gases, right? Now these molecules doesn't have any particular order. So liquids, when you go for the liquid or liquid crystals, the liquid which will have the properties of the solid. So similar to the gases, what you can say, you can just see this aspect here. So liquid and liquid crystal. So what it means actually. So schematically similar to this gases, you will find that liquids are not exactly in an order, but they resembles, they can assume they can take the shape of the containers. So and what you can say that they will have a bonding, and that bonding is weak when compared to the solids. So now we'll just go to our main topic, that is crystals. So you already know that solid is consisting of atoms and molecules or the ions, right? And which are moving from one another from its equilibrium position. So now the solid can be classified into three important categories. So crystalline solids, polycrystalline solids, or the next one is the amorphous solids, right? Here you can just see this. Solid materials have been classified into crystalline, polycrystalline and the amorphous. So when we go for crystalline, so again these crystalline solid, you can have a classification of single crystal and polycrystal. I have given you the last slides also. We have seen this. This is the example of single crystal. This is the example of polycrystal, and this is the amorphous. We'll just say that that is a non-crystalline solid, right? So now later in the section, we just had a very clear idea regarding the crystal formation, how the atoms are arranged here, how they are closely packed with each other, and how they form a perfect structure, right? So when we talk about polycrystalline, you can just see this. So in the polycrystalline, each atom will be surrounded by the boundaries. Right? You can just see this. This is I'm talking about this boundaries, right? So each atom is surrounded by a particular well-defined boundary. So that is thematically, you can just see this diagram. So now this is the dimensions. See, usually these have the dimensions of 100 nanometers to the 100 microns in the diameter, and the polycrystal grains are less than 10 nanometer in diameter. If this is the condition of the grain, if the grain is of the order of less than 10 nanometer in diameter, then we'll just call such grain as nanocrystalline. So amorphous, just we have seen in the amorphous, when you see the amorphous, see amorphous materials have been having some atomic or molecular dimensions. So what is this atomic and molecular dimensions? So these atomic and molecular dimensions are nothing but just take an atomic distance. It will be in the order of 1 angstrom. So that is 10 power of minus 10 meters, right? So amorphous materials, they doesn't composed of randomly oriented the constituent particles, and you can just see this, they are randomly oriented. There is no perfect sequential order of arrangement of the atoms are not there. Here you can just see it, and here you can easily view the schematic diagram of the arrangement of these atoms or molecules or the ions, and ultimately you will get this type of structure, and this structure is amorphous solid. So now this is about the crystal solids and their classifications, different classifications. Now what is actually the crystallography? So crystallography deals with the branch of science, deals with a geometrical see, whatever we are describing, that is a geometric description of the crystals and how they are arranged inside. So this is the overall view of, see, the different crystal. You will find the schematic diagram represent different crystals which are available on the earth crust. Like this you will find different types of crystals on the earth crust. So this is crystallography is very important in the case of solid state physics. So now the basic knowledge of this crystallography is needed to know the exact structure of the crystal. You can just see this. Why we want to know the crystal structure? Actually our aim is to find out the properties of the crystal. Once you know the properties, then you can use that particular properties for the application point of view. So we here as an engineer, we need to go for the application, right? So when you talk about application, definitely you'll try to first of all understand what is the basic concept behind the, or basic principle behind that particular element, right? So now here, so before going to this crystal lattice, you know that elementary crystallography is the basic crystallography which deals with the arrangement of the atom, how the atoms will be arranged. So we need to consider some important aspect. So what is that important aspect? Crystallography. So here we have just, you can just see this, we have taken an example of platinum crystal, and in that platinum crystal we have shown you the surfaces of the platinum crystal, how these atoms will be arranged, and this been shown with the scanning tunneling microscope. This particular structure, whatever you are seeing in the second diagram, is by using what you can say scanning tunneling microscope. Now crystal lattice are the structure of platinum. Inside the platinum, how the arrangement of the atoms will be there, and how this arrangement of the atoms by which we can form the smallest geometrical figure, that is in the form of a cube. So now this is the actually we need to understand what is actually we are talking about. We talk about crystal lattice. So crystal lattice is an imaginary thing, and that imagination has been shown schematically with an example of platinum. So I think that you got an idea regarding the crystal lattice. So we have just taken this particular aspect here regarding crystal lattice. Geometrically you can just make a what you can say, draw a diagram such that you will understand mathematically how this crystal lattice look like, right? So now when we go to the next aspect, so we need to, first of all we need to know what is actually the crystal structure. So for crystal structure we have just taken the crystal lattice and basis, and when you combine this crystal lattice and basis, then the question arises, we just understood what is crystal lattice and what is actually the meaning of basis. So if I associate these imaginary points with the constituent particles which are present inside the crystal, what is the constituent particles which is present inside the crystal? That is actually the ions, molecules, or the atoms. So that is what we are interested in. So when you just combine it, whatever the image or the schematic diagram, you will see that figure, that particular figure resembles the structure of the crystal. Now you can just see this is a geometrical view of the basis, right? So we are not going inside it. So now when you say about crystal lattice, what is crystal lattice? The crystal lattice is nothing but it has been classified into Bravais and non-Bravais lattices. So what is the concept of crystal lattice given by the scientist Bravais? So therefore we have to study about the Bravais lattice and the non-Bravais lattices. So now if the atoms are, see, you can just see the first diagram. If the see, you can just see these are let us consider these are atoms, and the arrangement of the atoms are in this particular fashion. When you arrange these atoms in this particular fashion, so whatever the atoms you'll find that the atmosphere or the environment about each atom will be same with respect to the neighboring atom. So we'll call such arrangement as the non-Bravais lattices. What is non-Bravais lattices? You don't find that the consecutive two neighboring atoms will have the same environment with respect to the other. This has been shown with respect to the this particular structure. You can just see this particular structure. This is a value that is given to you, very sequentially arranged atoms, and here you'll find a blue circles or spheres. So now this particular atoms are arranged, and the difference in between them, you can just see the first diagram, and when you compare with the first diagram with the second, you'll find that the environment about any 2 points is not same. So therefore this is called non-Bravais lattice. So now this is the types of crystal lattices. Again, we have taken the example, one example you have taken in niobium film, and that has been viewed microscopically, and it has been seen that these are nothing but this is the arrangement, and this is the source from where we have taken the this particular picture. So now this particular picture resembles the arrangement of Bravais lattice such that the environment about each point with respect to the other is identical. Now this is about the, and this when you consider a non-Bravais lattices, you can just see non-Bravais lattices in the form of honeycomb, where you'll find that the environment, you can just see this two spheres, red spheres, and in between the two spheres you have a blue sphere. So here that is representing the atoms, and here the arrangement of atoms are not identical, but the environment is completely different when compared with the Bravais lattices. So if this is the arrangement, if the arrangement of the atoms or the molecules or the ions are in this particular fashion, so we'll just call this type of arrangement of the atoms is come under the category of non-Bravais lattices. So now this is the what you can say. So when I say identical, so what is a mathematical function come into existence, that is translation lattice vectors. So we have just taken the translation function. What the translation function says? The translation function says that the any thing which is repeated infinite number of times, so we'll call such function is, and when you repeat it, it will be identical. So we'll call that particular repetition of the lattice points, or the mathematically a function has been repeated, and that you will get an identical value. So we'll call such function in the mathematics as translation. So we'll just for your reference, we just consider it as translation lattice vectors. So now this is two-dimensional lattice vectors, and when you combine this lattice vectors, right, you will get this particular structure. It has been shown with the schematic diagram of a cube. You can just see this cube, and here A, B, C indicates the dimensions with respect to three directions, right? X-axis, Y-axis, and Z-axis. If you consider X-axis, the distance between the consecutive origin to the axis considered to be a unit vector A, and the consecutive angle which is formed between the two normals is alpha here. You can just see this is the dimension B, and the consecutive angle which is formed in the negative direction, you see that is not exactly negative, but here, so you can just see if I extend this particular line to this direction, whatever the angle I am getting, that is called beta. And here also, when you see this is in the Z direction, so the angle which has been extended, that is called gamma. So you can just imagine that we are talking about alpha, beta, gamma, A, B, C, and this combination of parameters, lattice parameters, will say the combinations of dimensions of unit cell A, B, C, alpha, beta, gamma are nothing but they are called the lattice parameters. So when you combine these lattice parameters, once we can know the type of crystal which is available on the earth. Because for example, you can just see this. If there on the surface of the earth, you find out you want to find out which type of crystal you have chosen. So I don't know what type of crystal it is. So I have just taken on the surface of the earth some crystal, and I need to find out that value. So mathematically we can calculate by means of this lattice parameter. We can know if the dimensions and the angles are have satisfying a particular condition. We can say that particular crystal come under which crystal system. That we'll discuss in the later section. So we had just discussed about the different Bravais lattices in 2 dimension. In 2 dimension Bravais lattices, see, when I say Bravais lattices, what is the meaning of Bravais lattices? It means that when you compare an atom with respect to the corresponding atom, the environment about that particular atom with respect to other is identical. I will say that that is called Bravais lattices. In 2 dimension, you'll find that the how can you arrange, if you arrange in this particular fashion, you see fashion 1, 2, 3, 4 and 5, such that you'll find that the environment with respect to the neighboring atom or the molecule or the ion is identical. So if this is the case, we say this particular arrangement as Bravais lattices. So indeed in 2 dimension, you can just arrange in this particular fashion the Bravais lattices, and such that the environment with respect to the neighboring atom or a molecule or ion will be identical. So now, what is the smallest geometrical figure which can be obtained by the 2 dimension? You can just see this. See, this is the smallest what you can say square. You can be see this is square. You can just see this is a square. The smallest geometrical figure which has been obtained 2 dimension is square. And when you go for the 3 dimension, right? When you go for 3 dimension, you can just see the small cubes. You can just see this is schematic diagram which represent the small cubes. So this is the unit cell. You can just see how these unit cells have been joined, and this collection of this unit cell resembling the total crystal. So unit cell in 3 dimension represent in this particular fashion. So you can just see this. This is unit cell, and the combination of this unit cell is actually starting from here. Atoms, molecules, and these atoms and molecules will be arranged at the corners of the unit cell, and these combination of different unit cell in 3 dimension will give rise to the exact crystal structure. So now this is the case. So how many common unit cell you'll find in the cubic crystals? See, whenever we talk about a crystal system, the crystal system will start with the first crystal system, that is called cubic crystal system. In cubic crystal system, you can arrange 3 types of unit cells such that the environment about each point will be identical. So how we can arrange? This is called simple cubic, this is called body centered cubic, and this is whatever you are observing here, this is a face centered cubic. So this type of 3 types of Bravais lattices can be arranged in the cubic crystal system, which is being viewed on the screen. So that is what we require for the cubic crystal system. So we just say that there are 2 types of unit cells here, primitive unit cell and non-primitive unit cell. So if you find that other than the corners of the cube, if the atoms or the molecules or the ions are arranged other than the corners of the unit cell, then we say that is unit cell is come under the category of non-primitive or non-conventional unit cell. Now this is the what you can say arrangement of the lattice parameters. Well, you find that A, B, C, alpha, beta, gamma are nothing but they are called as the lattice parameters. You can just see A, B, C are nothing but they are the lattice constants or the dimensions of the unit cell, and alpha, beta, gamma come under the category of crystallographic angles, or we just say that is interfacial angle. Now for your reference, we have shown you the figure. You can just see this type of figure where you will find that the unit cell will be. So now this is the case for the primitive and primitive unit cell. So now see why we call, if this particular lattice parameter condition is satisfying, we just say that this come under the category of cubic crystal system. You can just see if the dimension A is equal to B is equal to C, and alpha is equal to beta is equal to gamma is 90 degrees. So we just say that that particular crystal will come under the category of cubic crystal system. So now like this, how many different crystal systems which is available on the earth crust? You have 7 types of crystal system which is available on the earth crust, right? So this is called cubic. If this condition is satisfying, this particular crystal system will come under the category of cubic. So tetragonal, orthorhombic, hexagonal, monoclinic and triclinic. So this particular 7 crystal systems, trigonal also. So 7 crystal systems are available on the surface of the earth crust, which are very important for industrial applications and also for an R&D department. So for research and development also, you will have a different application. So an engineering student should understand the need of knowing the concepts of different crystal systems and how these crystal systems can be used in industries for manufacturing of different equipments and devices, and how these particular crystal systems are being now also is used in the research and development for research and development purposes, and how a layman should know these particular concept, and how it is indirectly is very very important for a layman to understand this particular concept. So I think that with this we have just concluded the 7 crystal systems. And see, when we just go for the different direction, what is the meaning of direction here? So see, in a crystal system you will find there is a concentration of atoms will be there, and you will find empty space and also concentration of atoms. So we need to locate that where actually the concentration of atoms are is there inside the crystal, and where the empty space is there. So as that, so why actually we need to look into this particular aspect is that why, because we need to know the properties of the crystalline solid or non-crystalline solids, or the amorphous, if you talk about amorphous. So now what is the need of studying this thing is that if you know the concentration of the atoms, where actually the atoms are residing more, so then you can easily understand the properties. Once you know the properties, then you can know that how this particular crystal can be used for various applications. Now that is the need of studying about the crystal directions. So now, so these are different examples which has been given to you. So these crystal directions are nothing but the scientist known as Miller. He has introduced the mathematical way to locate these crystal directions. So Miller has introduced a mathematical way to locate this crystal directions. So once you know the crystal direction, then you can incident the electron beam or neutron beam, or you can X-ray beam, in order to know the exact structure of the crystal. Once you know the structure of the crystal, then there will go for the different diffraction, X-ray diffraction, from which we can know the different properties of the crystal. So now this is about the see, you'll find that definitely when you talk about a crystal, so you'll have a direction. So that direction will be maybe positive or it may be negative. So now this is about the Miller indices. Just now we just discussed that knowing the Miller indices we can locate the crystal direction. So once, so how we can what is actually the Miller indices? It is the, see, you can just say it is a vector representation or the orientation of the atomic planes, right, inside the crystal lattice. And this can be also known as a smallest geometrical smallest geometrical ratio which has the same what you can say, the intercepts will have the same value with the, as with the reciprocal with the corresponding crystallographic axes. So how I can know the Miller indices if I know the semantic diagram of the crystal. So now how to determine it? So first of all, we need to determine the intercepts of the given plane. So what is the definition of plane here? Plane means the, let us consider for our reference and for our comfortableness, when we talk about a plane, so we just consider the cube structure. So when you assume a cube structure, so the faces of the cube will be 6. You find that 6 faces of the cube. So each face of the cube is considered to be plane. Let us consider that each face of that cube is considered to be plane, and that particular plane is intersecting. If it is intersecting to a particular axis, either it may be x-axis, y-axis, or z-axis. So if it is intersecting, then just you have to determine the intercepts of that particular plane along the 3 crystallographic directions or the axes. And whatever the intercepts you got now, that intercepts should be taken as the reciprocals. When you take the reciprocals of the intercept, then you need to simplify that particular reciprocals. Now how you will simplify it? For example, you got the intercept as 1 by 2, 1 by 3, and 1 by 4. So whatever the numbers which are there in the denominator, either it may be 2, 3, 4, you just take an LCM, and whatever the LCM value you got, that LCM value should be multiplied with the reciprocal fraction value, and whatever the simplified value you'll get, that simplified value will be considered to be Miller indices. And these Miller indices are not being represented with the commas, they are represented only with the numbers, right? So if you just represent this particular values with the commas, then that is not called indices, but they will be considered to be the points. You can just see this is 1 comma 0 comma 0, and if it's here, when you see this is the point, I'm talking about a point here, when you see the Miller indices, these Miller indices are not separated with the commas. They are, why? Because they represent the planes, right? So now this is the example we have given, I have already shown to you. So this is one of the example how to calculate the Miller indices by considering this plane. So I've just told you in the previous section that plane is being considered to be the one of the face of the cube. So you just see this, this is one of the face of the cube, you got the Miller indices. So now this is different examples of the Miller indices. Now you can just see this cubic crystal system. In the cubic crystal system, we can arrange the lattice points such that the environment about the lattice point will be identical. So how many ways the constituent particles will be arranged? 3 ways. That is called Bravais lattice, a simple cubic, body centered, face centered. So hexagonal, you'll find only SS means simple cubic. See, S is simple, base center, BAC base center, monoclinic, orthorhombic. You'll find 4 different Bravais lattices. This is the way that you can arrange the constituent particle such that the environment about each point or each atom with respect to the neighboring atom will be identical. Now this is the crystal system, and whatever been shown in the bracket, that is actually the Bravais lattices of the crystal system. So now this is what we have studied in the previous section. So now with this we just have completed our chapter 1 revision. So this was the revision which we have just completed it. So now we just start with the Frankel defect. So before going to that Frankel defect, see, we'll just start our Frankel defect. So in the previous class, we just started with the Schottky defect. Now we'll go for the Frankel defect. So now in the examination, we just ask you what is the equilibrium concentration. See, equilibrium, just a minute, equilibrium concentration, derive the equilibrium concentration of Frankel. This has been asked in the examination twice, so this is very, very important. So if you have any doubt regarding it, so please let me know, right? Such that I can repeat this particular class again. Right? So we talk about Frankel defect. So what you have to write in the, see, whatever I'm writing here, directly you can write as it is in the examination. So whenever you need to whenever you are in need of calculating any derivation, first of all, you should be very clear with the concepts or the sentences that you are going to write. So here, so first of all, what we consider, let us consider the ideal crystal. So what we are doing, first of all, we are considering that the crystal is identical. See, the crystal is ideal. So the crystal is ideal. So how many number of constituent particle find? We don't know. So therefore we'll write if capital N is the number of, you have to expand it. So number of atoms, that may be atoms, that may be molecules, right? Or that may be ions, right? It may be anything. So for our instance, we'll just go for number of atoms, N number of atoms, and small n be the number of Frankel atoms. Here, when you just consider the Frankel atoms, so first of all, what is actually Frankel defect? Frankel defect, you should know, right? Very briefly, what is actually the meaning of Frankel defect. So what is Frankel defect here? Frankel defect definition, see, this is for your reference. You don't write this thing in the examination. Frankel defect is the combination of vacancy plus the interstitial 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 atom. So this is the combination of Frenkel. So you'll find that here Ni with respect to n, and you'll find that there is Ni is also there, and capital N, if capital N is existing, then capital Ni will also be there. So now here in Frankel defect, you'll find that the Frankel defect definition is vacancy plus interstitial atom. So the combination of this will give us the Frankel defect. So now we just move on to our Frankel defect. So in the Frankel defect, what you'll write here is that capital N Ni. See here what we are going to write here. See this is what Ni. See instead here you'll find capital N is the number of atom. Ni you will find the extra term Ni. This is due to interstitial atoms. So this is the extra part that we have to consider when you just derive the equilibrium concentration of the Frankel defect. Right now, so which concept we have to use here? Now we just see by using the Frankel. See by using the by using this what we have to derive here, Frankel just a minute, by using which particular mathematical concept we have to use here, right? By using the, just in the shortcut effect also we just use the which concept, probability concept. Here also we are using the probability concept. So what the probability concept says, that if you don't know exactly how many number of atoms are there, if you don't know there is a function, you know that there is a function, but you don't know what is actually happening inside the crystal. So exactly if your accuracy is not applicable for that particular function, then we have to use this probability concept. And the probability concept say that we have to use the permutation and combination concept, where you'll find that here vacancy, instead of vacancy you can see this is vacancy plus the interstitial atom. So P in n factorial divided by how many? N factorial. So what is remaining here? Capital N minus small n factorial, right? So now this is multiplied with capital N I by small n factorial into Ni minus n factorial. You can just see this. This is the aspect that we need to understand here. So n factorial and Ni minus n factorial. So this extra term is coming due to this interstitial term here. You can just see this is interstitial term. So here we'll the same. What we'll do is that we'll apply the same concept here. So what is entropy? You know that entropy is given by K log P. This is equation number 1 and this is equation number 2. Very simple. So what you need to do here is that first you just take this log. When you take log P, separately you can take this log of n factorial. First we'll just write as it is, n factorial into capital N minus small n factorial, right? Then open this big bracket into Ni factorial by small n factorial into Ni minus small n factorial. Now this is closed and a big bracket is there. So here what it will be? Log A into log B. So you already know that the formula for log A into log B. So that is actually equal to log A plus log B, right? So now, sorry, log B, right? Log B. So log A means separately you can just do this log of n factorial by small n factorial. This we have done in the shortcut effect also. So right, and this is what? Plus log of Ni factorial by small n factorial into capital Ni minus small n factorial. Now this is the term that has been splitted, and individually you can just do this. See, individually we can just do it as we have done for the shortcut effect also. N factorial by small n factorial into capital N minus small n factorial. So I think that this resembles the same shortcut effect what we have done. See, log n factorial, right, minus of log n factorial minus directly I'm doing it. So log of n minus n factorial. So we are just taking this first term here. We just expanded the first term here. So next term will be the next one. So individually we'll do it and then we'll add it, right? So here the next term, what is the next term here? Log of ni factorial by n factorial into ni minus n factorial, right? Now this can also be written as log ni factorial minus log of n factorial minus of log. So why I am writing here minus twice? You can see this log a by log b into c, that can be written as log a plus log b into c minus log b into c. So minus will go inside. So minus log b minus log c. Now this is the term we have expanded. Now what is our aim? Next aim is to remove this factorial. So in order to remove factorial, remove this factorial, right? What we will do? Factorial is this one. So we take the help of we use Stirling approximation. We'll go for Stirling approximation. So what the Stirling approximation says? What it says that wherever you'll find the factorial term log x factorial, that can be written as x log x minus x. You can see this. So if the factorial function is there, whatever the term is there, so you can just write this term in the very simple form. So if you find that log n factorial is there, so that log n factorial can be written as n log n minus n. Very simple. And wherever you'll find log n suffix I factorial is written as n suffix I log of n suffix I minus ni. Now you can just see this, this is the term that we expanded. We have removed the factorial term. So similarly you can just write it down for the log n also. Log n factorial can be written as, by using Stirling approximation, n log n minus n. And this is for log of the other term is n suffix I into n factorial can be written as n I suffix minus n into log, see, as it is, whatever thing which is there, what parameter is there, the same parameter you have to repeat it. And so this is what minus ni, right, minus ni minus n. Now this is the value that you get for this term. So this is the expansion that you need to do while writing expanding the term which is represented with the factorial. So I think that this is the way that you have to start with the Frankel defect. So if you have any doubt regarding this, again we'll just repeat this derivation in the next class, right? Thank you everyone. Thank you for your patience. So right, with this we'll just conclude our talk, right? Thank you.